Alright, I have a little time left here. Swim in rising waters. I've previously solved it, I guess. Hard. You're given an n by n integer matrix grid, where each grid ij represents an elevation point ij. Okay, elevation map. It starts raining, water gradually rises over time. At time t, the water level is t, meaning any cell with elevation less than or equal to t is submerged or reachable. I see. You can swim from square 0 to another 4-directionally adjacent square if and only if the elevation of both squares individually are not at most t. Right. You can swim infinite distances in 0 time. Of course, you must stay within the boundaries of the grid during your swim. Return the minimum time you can reach the bottom square, n minus 1, n minus 1, if you start square 0, 0. You can start from any square, you can swim to adjacent squares. So 0 starts raining at time t, the water level is t. So time 1, it's this. So you swim here, time 1, time 2, time 3, so it takes 3 time. Okay. So here 5, and then it takes time 16 to get here. 17, 18, 19, 20. So it's actually better to do wait here at till time 20 and then 21. Nope. Final route. The final route is shown. You need to wait until time 16 so that 0, 0, and 4, 4 are connected. Oh, it takes, you can swim infinitely. I thought you can only swim one at a time. Okay. Nice. I see. I think I see. So it's like you can swim up to here, time 15, and then time 16 you can swim all the way to the end. Interesting. Okay. Okay, I think this should be doable. I think I need to maintain a matrix to indicate where I've been, and then probably a stack, no, a heap. Yeah, I need a heap. Yeah, I think I need a heap. So this heap should be like that. It could be maybe a deck, because I think I need to keep track of the lowest amount. Add the adjacent stuff that is next to the current places that I've been to. Okay, so it'll be something like heap, maybe 0, 0. I'll say time is initially 0, and then available, or say reach is how far I can go, or which cells are available given a matrix. So it's a reach matrix. So rows, columns is length of grid at 0, and then reach is false everywhere. False times the number of columns. for every row. And then recheck 0, 0 is true. So you start there. So what am I going to do here? Let's say while heap row column is the top heap. So we heap pop, I guess. Heap pop. Can you actually have duplicate heights? Each value in grid is unique, so you can't have duplicate heights. Heap pop is going to be top heap. And then yeah, look at every adjacent spot in the matrix from this spot. So I'll have deltas for the neighbors. Will be one in each direction. I'll have a helper method for isValid location. Zero is less than or equal to r is less than rows, and 0 less than or equal to c less than columns. So I need to go in each direction and put that direction onto the heap. If it's not already on the heap, maybe I need to have two. Maybe have a set. It's reachable, and if it's an added, I guess maybe I'll have added. False times columns for every row. So for every change in row, change in column in my delta list, new row, new column is plus delta r, c plus delta c. If not is valid, let's continue here. And then or if it's already been added. No, I guess maybe I could actually extend the location, extend the boundary of added to be false, to be true at the, to be true on an extra boundary, and then I don't have to use the, I don't have to use I wouldn't have to use is valid. Okay, actually, let me try that. Added for every row in added, row.append a false or true. So that's like adding something that's true that I've already been to on this side. And then you add another row to added for that's on this side. And if I index from any square out of bounds, they'll actually go to one of those cells. So uh, added dot append an extra row that is all true. True times, I'll make this keep the dimensions like n plus 1, n plus 1, so it's true times columns plus 1, I think. And that should be a list, an array. Go ahead and just check to see if this works correctly. Print added. On line 22. So first case, this should be a 3 by 3. True, true, false, true, true, false, true, true, true. These are like out of bounds or seen. I guess I also need to set the initial location to be true. Okay. So if it's not, so I don't think I need this valid anymore. So if it's already been added, I ignore trying to add it again. And otherwise I add it. Guess. Huh. Wonder if I even need a reach. Can I just work on added? Yeah, I guess maybe this might be I pop. Okay. Let's say cell. Let's say height of this current thing is grid at this row and column. Yeah, this logic needs to be occurring before it. So 0, 1, 2, 3, 4, 5, and then the stuff that's been added should be like these cells and this cell. And this height should change time possibly. So time equals max of the current time and the height, right? And then I need to check that this is the end location. If bar equals rows minus 1 and columns equals cols minus 1, then return whatever time this is. If it's not, okay, yeah, I think that's right. I think that's it. If my current time is 16, I add this thing gets processed, popped in the heat. It doesn't change the time is still 16. And then I still need to add other stuff into the heat. Okay. So if it's true, then move on. If it's not true, then added at nr nc is now true, and I need to put this on the heap. Heap push onto the heap, the tuple that is this row and column. Oh no, okay, I see. I need to put the time into this tuple, otherwise it doesn't know how to sort. So the time should be a tuple. The heap should have tuples of time slash the height of the thing, which corresponds to the time of the thing. Row column. Okay, and then this should be time of this thing, which should be grid at new row, new column. And then it just pushes a bunch of stuff, and that should return whatever. It should return within the while loop. Too many values. Oh, oops, this should be. Okay. This index out of range. If added nr and c is true. Oh, really? Oh yeah. Really? So I thought added should be 3 by 3 at that point. How is it going out of bounds? Negative 1, 0, negative 1, 1. It's out of range. Oh, okay. Yeah, this is too many bracketings. Okay, I guess I didn't need the extra set of brackets here. Append. I guess this automatically makes a list. Okay. Oh boy. Oh, I guess maybe this thing looks like it doesn't have a starting height as 3 or 0. Oopsie. Starting height should be grid at 0, 0. Guess I kind of assumed that was the case, but obviously that was a poor assumption. So time should immediately change to that time. Okay. Okay. Alright, I guess I didn't need this reach. It's just basically added. Didn't need that since I had the out of bounds -1, or extended the size of the added matrix. I guess added is just, yeah, that's fine. Guess I could call it just reach then. I guess I'll call it reach. Yeah, whatever. Okay, we'll call it added. Time is 0. Rows and columns. Guess I can probably set time to 0 down here. Move the delta one up here. And the constant type variables up top. Maybe the heap. So this is the added stuff, the initial added stuff. And this is the initialization stuff. Heap pop time for everything. Okay, yeah. Yeah, this seems, I don't know, this seems like a medium problem rather than a hard. Well, there wasn't much to it besides using a heap. I guess you use a heap plus another matrix to keep track of where you've been. This feels like a medium. Okay. This is kind of an early numbering. Okay, so summary here, this is going to be use a matrix to keep track of what areas explored. Use a heap of tuples height row column to prioritize exploring the next lowest elevation tile. Whenever exploring a tile, update the time to the tile's height, which corresponds to the earliest time it's available. If that time is bigger than current time, add a current time variable, let's say initially 0. So if the first tile is like tile time 3, then that means time becomes 3 if time is currently 0, because you have to wait until time 3 to do it. And since you're using heap, there's no earlier time that you could get to, or there's no other tile that you could get to before then, because this is the earliest height in the heap. Get the smallest height from top of the heap to explore. Whenever exploring a tile, update the time to and then check to see if it's final tile and return if it is. Return current time if it is. Then process the unexplored locations adjacent to that tile and add any unexplored tiles to the heap. Again, also setting the location to explored, or I call it added Actually, maybe this should be called explored is fine, actually, rather than added. Small optimization to not check for out of bounds indexing like row can add an extra dummy column row at on the outside of matrix that is of explored matrix that is true, so that it prevents those cells from being added to the heap. So initially explored is set to the same size as the initial matrix, and then I add an extra column of true at the end of each row, an extra row of true at the end of the matrix itself. So therefore, when I do the delta DRDC, if it would change the row and column to be something out of bounds, then it'll just hit the true cells within the explored matrix. Anyways, time complexity is going to be O of mn, where m by n is the dimensions of the grid, and then each tile in the grid is added to the heap at most once due to the explored check. You only do stuff if it hasn't been explored. And since there is constant work in the loop, there can only be at most n by n cycles of the loop. So plus is O of n by n. And then, oh, whoops, actually the heap stuff. Well, it's not constant work. So of mn log mn. No. Each tile on the grid is added to at least once, and the cost of the loop is based on the cost of adding an element to the heap, which should be O of log k, where k is the size of the heap, since the size of the heap is most nn. Thus, cost of adding to heap here is O of mn, O of log mn. Thus, overall, it's O of mn times log mn. Space complexity, this should be O of mn to maintain the heap and to maintain n, the overall size of the reach matrix, or the explored matrix, which is a 2D matrix size m times n, and the heap can have up to m times n elements.